Hello viewers, in this video I will discuss about the term electric flux. First, what is a flux? Flux is something that appears to pass through a surface or a substance. So that we call it as generally flux in physics. Okay, then what is electric flux? So electric flux is the number of electric field lines that pass through a surface in perpendicular direction. Okay, so electric flux is the number of electric field lines, passing through in perpendicular direction to the plane surface. This we call it as the electric flux, number of electric field lines. So if we have a plane surface like this and I have electric field lines flowing like this. So what is the number of field lines or the field line intensity in this particular plane surface? So that too, the electric field line direction are considered perpendicular. Okay, so now what is electric flux notation? So it is given by phi E. So this is flux with the notation of E, it means that it is electric flux. So it is given by electric field vector and area vector. So this term, this A is notated as area vector. So what is area vector? So here, what is this area vector? So if I have a plane like this, so this magnitude is given by, so we know that a vector has both magnitude and direction. So magnitude is given by the area of the given figure. So the direction is given perpendicular. The direction is given perpendicular to the plane surface. So if I have a plane here like this, so this direction perpendicular. So area vector, so that magnitude is the area of the given figure. Okay, whatever maybe the figure we are considering, whether it is a square, rectangle, depending upon the shape, that is the area magnitude considered. Direction, the area vector direction we are considering perpendicular to the plane surface. Okay, so that is the totally we call it as area vector. So now we will see what is the area vector representation for a 2D surface and a 3D surface. Okay, so we will consider area vector for a 2D surface. Okay, so if I have a representation like this, x, y and z. Okay, now here I consider a square of side A. Okay, so you know that area of square we could be represented as a square. This is the magnitude. So what with respect to direction? So area vector, it is given by, see the direction here, that is here it is taken outside direction because perpendicular to the plane surface, either this direction or inverse this direction, like hitting with the hammer. Okay, it will move inside in this particular direction, inwards or outwards. Okay, whether which case we have to consider for the 2D surface. We know that this 2D surface, the 2D surface, it is a open surface. 2D surfaces, they are open surfaces. Okay, so one most important point about area vector is, in area vector the directions are, that is only the outward directions are considered. Only outward directions are considered for a plane surface. See, area vector, the directions, only outward directions to the plane surface are considered when we are representing the area vector. Okay, whatever may be the surface. Okay, so in case of 2D surfaces, see, we have noted down that. So we have noted down that this is a open surfaces. 2D surfaces are open surfaces. Okay, so you know that they are open surfaces. So in case of open surfaces, both directions, they represent the outward directions only. So when we have a plane like this, both directions outwards, both directions are outward directions only. So both directions could be considered. So see that in this particular area we have k cap as the directions. So this one, a square minus k cap, also could be considered. Okay, both represents the area vector for this particular square shape. Okay, because it is a 2D surface. In 2D surfaces, both directions are considered. Okay, so similarly, we have another example. So if I have like this x, y and z. Now I am representing a circle in your x and z direction, representing a circle in x and z direction. Now see that this area vector will be pointing either in this direction or in this direction. Both are considered because it is an open surface. The both direction represents the outward direction only. See the value area vector for this particular, the area vector here, it is considered, see, as a circle it is pi r square j cap, either plus or pi r square minus j cap. Okay, so both are considered for the squares. Okay, both are for a circle. Both areas are could be considered for a 2D surfaces. Okay, so now, so we have given it for a 2D surfaces. So how we are representing in case of a 3D surface? Okay, now we'll see how we can represent in case of a 3D surface. Okay, so area vector for a 3D surface. So see, x, y and z. So see that when I consider, see, when I consider this particular plane, when I consider this particular plane, we know that for area vector, we know that the area vectors are represented only in the outward directions. So here, this will be the only direction. Okay, for this particular plane, this will be the only direction. Okay, for this particular plane, this will be the only direction because the 3D surfaces, they are closed surfaces. They are closed surfaces. Okay, so for the consider this particular plane, this will be the direction of the area vector. Okay, so this will be the representation of the area vector in case of your 3D surfaces. Okay, so similarly we have a cylindrical surface like this, a cylindrical surface like this. Okay, so this will be the direction of the area vector. For this particular, this will be the, so all are outwards. So only one particular direction are considered. Only one particular directions are considered for a 3D surfaces. Okay, for 2D, both directions are considered because it has one, it is an open surface. So both directions are considered. But in case of 3D surfaces, only one direction is considered for representing the area vector. Okay, so this is about the area vector. So now we will move on to the electric flux formula. So we talked a lot about area vector without talking about electric flux. Okay, so now we know that this is about electric flux, area, electric field vector and area vector. Okay, so now we will see that I am considering a plane like this and this could be the area vector. Okay, so if I have electric field coming in this direction, this particular direction, if I have electric field in this particular direction. Okay, so imagine that if the electric field and area separated by this angle theta. Okay, we know that electric field considered are only perpendicular to the direction of the plane surface. The electric field considered are to represent electric flux is only the electric field perpendicular to the direction of the electric field. Okay, so which component is perpendicular? So here we have E. Here we are having component E cos theta. So this component is E sin theta. So this E sin theta is not perpendicular. It is something going towards the plane surface or parallel to the plane surface. So that is not considered. That will not contribute to the electric flux. So the only contribution is only the value E cos theta. So the electric flux formula is written as E A cos theta. Okay. So depending on the value of theta, the flux changes. So if I have a surface, a plane surface like this. So this is the normal vector A. And if I have electric field going parallel like this. So in such cases, we see that electric field and the area vector both are parallel. Okay, in such cases, we have theta as 0. So what could be the flux now for this particular? It will be EA cos 0. That is nothing but only EA. That is nothing but only EA. So if I consider a surface like this and the electric field is going in this direction means, sorry, if I have a surface like this, and we have electric field going in this direction, so we have area vector in this direction means, now for this case we can say that the angle will be, theta will be 90 degree. Okay, in such cases, because what is theta? The theta is the angle between the electric field and the area vector, between E and A. Okay, so if I have theta as 90 degree, the value becomes 0. I don't have any electric flux. Okay, so this is the representation of the term electric flux. So unit of electric flux, here it is Newton Coulomb in a meter square. So this is the unit of the electric flux. Okay, so depending upon the value of theta, we can see that there is a changes on your electric flux. So for just a small model, so imagine this as your electric field and this as your plane surface. So right, okay, so yeah, so now I'm going to place a plane surface on this. So now we see that all the electric fields are not touching this plane surface. So what is electric flux? Only the electric field lines passing through this particular plane surface. Okay, so that we called as electric flux. So this when I tilt this particular surface to an angle theta. Okay, so depending upon the value of the angle theta, the flux changes. So this is the just a small representation of how the electric flux changes with respect to theta. Okay. So this is about electric flux. Okay. So based upon this electric flux only, we have next the explanation of Gauss law and its applications. Okay. Thank you.